start with some announcement and with welcoming you to what is the last tea break of this year. So I will actually be welcoming also on behalf of the GGI director, Stefania De Curtis, who unfortunately could not be here right now, but she asked me to extend her welcome to all of you, and also to thank you very much for attending not only this one, but all this series of colloquia, which has been very successful. Thank you to the great participation. I would also like to tell you that there is a break for Christmas, but we will be coming back in January. And in particular, I'm very happy to announce for the 19th of January, a special GGI Tea Break dedicated to Steven Weinberg and his legacy, with a very exciting lineup of speakers, Nimar Kaniamed, Riccardo Barbieri, Howard Georgi, and Edward Witten. So I hope that you will be able to attend also that very nice event in January on the 19th. On top of that, even if the tea breaks will be suspended for the Christmas period, we will have actually at GGI some other event on the 20th, 21st, and 22nd of December, so Monday to Wednesday next week. That's the Avogadro meeting. It's a meeting of young researchers that we will give interesting lectures on new trends in theoretical physics. And while it's too late to attend in person, you are very welcome to register to attend virtually and to follow the lecture virtually. Now, with this little bit of housekeeping out of the way, let me introduce today's speaker. And it's a particular pleasure because not only is a very distinguished physicist, but he is also a colleague of mine at the Padua section of INFN. So it's a particular distinction for me to be able to call him my colleague. And the speaker for today is Dima Sorokin. Dima is a very renowned expert in several aspects of string theory, supersymmetric field theories, and quantum field theory. In particular, he did his PhD in Kharkov. He obtained it in 1985 under the supervision of Professor Volkov and Professor Tkach. And he has done work on several aspects of strings, fields, and supersymmetry, in particular aspects that are related to symmetries and dualities, for what concern in particular branes in string theory. Also, he gave very important contribution to the theories of higher spin. And more recently, his interest in dualities and symmetries found some very interesting applications in a very old theory, the theory of electrodynamics. And I think that this will be the topic of today's seminar. So without further ado, please, Dima, the floor is yours.
Thank you very much for this kind presentation and for the invitation to give a talk here. And let me try to share the screen. Okay, yeah, I think you. Perfect. Yeah, so I should say that this will be a kind of an outlook of a non-expert in the field of nonlinear electrodynamics, because I have entered this area quite recently and found that it is quite a wide area of research, ongoing research, and I realized that models of nonlinear electrodynamics have been extensively constructed and studied in the context of catching new physics, if one may say in these words. And for studying and tackling fundamental cosmological problems, for example, such as the physics of black holes, inflation, and dark energy. And it has also been used as an effective description of properties of certain materials in condensed matter physics and optical media, basically via the gravity, gauge gravity holography. And of course, the most known examples of nonlinear electrodynamics are, the first one is the Born-Infeld theory, which was constructed in 1934, and it was constructed with the purpose to avoid singularity of self-energy of charged point particles. But much later, it was found to be a very important ingredient in modern string theory. And another example is the Heisenberg and Euler nonlinear electrodynamics, which is an exact effective one-loop effective theory which describes effect of quantum electrodynamics, where the one-loop effects of electron-positron pairs have been integrated out. But then during the following decades, a variety of other models of nonlinear electrodynamics have been constructed and used for different purposes. And among them, there are very specific ones such as logarithmic, double logarithmic, exponential, rational, inverse, Einstein parallel law, and other electrodynamics constructed by and studied by different people. And probably the latest specimen of this zoo of nonlinear electrodynamics has been found only very recently by Igor Bandas, Kurt Lechner, Paul Townsend, and myself, and we call this theory ModMax, and we found it last year. And a remarkable property of this theory that is the unique modification of Maxwell theory that preserves all its symmetries, including electromagnetic duality and conformal invariance. But in this talk, I would like to make an overview of the properties of the most characteristic examples of models of nonlinear electrodynamics, including Heisenberg, Euler, Born-Infeld, so-called Belinsky-Zaharov and ModMax electrodynamics. And I will also try to flash some very briefly effects which nonlinear electrodynamics exhibit, for example, and manifest in physical phenomena such as vacuum birefringence, and briefly discuss the applications of these models in the context of gravity in condensed matter theory. So let me start first with, of course, very well-known example of Maxwell theory. This is basically only to set the notation convection and introduce the basic concepts. I don't know, this bar, how can I remove it from? Do you hear me?
I don't see the bar. So
you don't see the bar.
I think if there is a bar, you can
for example, is there a bar in the middle of the slide or not? This
no.
Okay, very good. Or I'll not. Okay, so of course, very well known Lagrangian of the Maxwell theory is the one presented in the slide. It can be written as in the Lorentz covariant form at the square of the field strength, or in terms of the electric and magnetic vectors, which are components of the electric field strengths. And the three Maxwell equations of motions are written here. They are combined with the Bianchi identities for the dual of the field strengths, and can be rewritten in equivalent form again in terms of the electric and magnetic field. Of course, this theory is Lorentz invariant by construction, but one can show that it is also invariant under the full group of conformal transformations. I will not show this, but only mention that to see that there is a conformal invariance here, one can make the rescaling of the potential field strengths with a certain constant parameter A, and then the coordinates of space-time with the inverse of A or vice versa, and then the action will be invariant. So this is a manifestation of conformal invariance. In addition, as is also well known, the equations of motion of Maxwell's theory are invariant under electric magnetic duality, which rotates the field strengths and its dual by a SO2 duality transformation with some angle parameter alpha. So upon these rotations, of course, the equations of motion remain the same. The Lagrangian and the action, they don't remain invariant, but there are formulations in which the duality symmetry becomes a manifest theory of the action, but I will not talk about these formulations here. Now let's pass to the generic properties of nonlinear electrodynamics. So the Lagrangian of nonlinear electrodynamics is usually taken to be a function of two scalar or Lorentz invariants, one scalar and one pseudo-scalar constructed of the field strengths of the magnetic field. So these are S and P defined in this way. And usually to avoid the presence of ghosts, the Lagrangian does not include derivatives of the process. So we will consider models whose action has this form here. Of course, well, a common assumption regarding the structure of this Lagrangian is that it is assumed to be an analytic function which can be expanded in the powers of the field strengths, and in such a way that in the weak field limit, in which the higher orders of the field strengths are less than f squared, then the Lagrangian reduces to Maxwell theory. But there are interesting models which don't satisfy this assumption, and among these models there is a class of conformal nonlinear electrodynamics, and which also includes this ModMax theory, which we'll see later. Of course, the structure of the higher order terms in this Lagrangian, they depend on the origin of the theory and the purposes for this theory was constructed. In particular, the value of the coefficients A and B differ from one theory to another. And let me give the example of the value of these coefficients for the Heisenberg and Euler theory. So here we have B equals 7/4 of A, and A is expressed in terms of the fundamental constants of the theory, where alpha is the fine structure constant of electrodynamics, mu0 is the vacuum magnetic permeability, and me is the mass of the electron. So one can see that the coefficients is very small, and that indicates that the effects of these quantum effects of electrodynamics are really very small, and it's hard to determine them in the experiment. In comparison, let me also present the values of these coefficients for the scalar quantum electrodynamics. So where instead of the spinor, we have a scalar charge, scalar field in the loops, then the coefficients change in this way. Okay, let's now consider another general properties of this nonlinear electrodynamics, Lagrangian. So usually once this theory to be physically well defined and imposes the conditions of causality and unitarity, and basically the requirement of causality and unitarity requires that the Lagrangian of the nonlinear electrodynamics is a so-called convex function of the electric field E. That is, that if we construct the Hessian matrix, taking the second derivative of the Lagrangian with respect to the components of the electric field, then it should have non-negative eigenvalues for all values of E and B. This condition of convexity is also important for the existence of the involutive Lagrangian transform to get the Hamiltonian formulation from the Lagrangian one and vice versa. Then, of course, the symmetries of these Lagrangian the obvious symmetry is the Lorentz invariants, but the conformal symmetry and duality invariants in general are lost. If you want to have a model which is conformally invariant, then you should require that the Lagrangian is the homogeneous function of degree 1, so that if we multiply S and P by a constant A, then it is equal to A times L. And so in this way, this factor can be cancelled by the rescaling of the measure in the action. One can also rewrite this Lagrangian in a form which looks like a Maxwell Lagrangian times some rational function of P and S. Even if instead we would like to have some nonlinear electrodynamics which has duality invariants, whose equations of motion are duality invariant, then we should derive a condition on the Lagrangian which should be satisfied for the duality invariance to take place. So in this case, the equations of motion have this form here, and they are again supplemented by the Bianchi identity for the field strands. And then if you want to have the duality invariance, that means that if we rotate this derivative of L and the dual field strands with the SO2 matrix, then we should get again a combination of some new field strands F prime and its dual, such that the new Lagrangian after the duality transformation depends in the same way with respect to F prime as the initial Lagrangian. And this imposes this differential condition on the form on the Lagrangian. This condition, I think, was first derived by Belinsky-Zaharov in 1983. This in his model in his paper where he studied the Born-Infeld theory. And the most famous example of the duality invariant nonlinear electrodynamics is Born-Infeld theory. Its Lagrangian has, again, the very well-known form. I write in two different ways. So the most economic way is to write it as the square root of the determinant of the metric plus the field strands of the electromagnetic field, or one can expand the determinant in the power of F and get this expression. Or then if we restrict the Lagrangian to the fourth order in the field strand, that it takes this form here. And T is the dimensional parameter of the Born-Infeld theory, which has the dimension of energy density. In string theory interpretation, the T is the tension of the D3 brane on which the open strings end. So, as I already said, it can be shown that the Born-Infeld theory satisfied the duality invariance condition, as was shown by Belinsky and Euler, but it is not conformal, of course, because T is the dimensional parameter. But its weak field limit is conformal. It is just the Maxwell theory. So the weak field limit of Born-Infeld electrodynamics is equivalent to taking the tension T to infinity. And one can immediately see from this line here that we get the Maxwell theory. And then one may ask what happens if we take the strong field limit. The strong field limit corresponds to the taking the tension to zero, but we immediately see that the Born-Infeld Lagrangian then becomes purely imaginary, but the total derivative, because it's proportional to F mu nu times F mu nu dual. So basically, the action vanishes of this limit. But it turns out that this strong field limit can be taken in the Hamiltonian formulation of Born-Infeld theory, as was noticed by Belinsky-Zaharov, and in this way he got his theory of electrodynamics. So let's have a look how it goes. So we compute the Born-Infeld Hamiltonian using the Legendre transform from the Lagrangian. To this end, we should introduce the momentum, which is conjugate D, which is conjugate to the vector potential A of the gauge field, and which is called electric displacement vector. And then invert the relation between D and E, which are written here, and get the expression for the Hamiltonian, which looks as follows. And now we see that we can easily take the tensionless limit, which is well defined, and get the Hamiltonian, which is the modulus of the Poynting vector, basically, the vector product of D and D. So, and this is the Belinsky-Zaharov electrodynamics, which is quite remarkable theory on its own, because it has the following properties. It describes all possible electromagnetic fields, which are called null fields. For this, the null fields are the fields for which the F mu nu times F mu nu is equal to 0, and F mu nu times F mu nu dual is equal to 0. These fields include the plane waves, for example. Then this theory is conformal, which can be shown, and it also has the, it is invariant under electromagnetic duality, but the enhanced one. It is now the group of duality transformation enhances to SL2R group. And finally, as Belinsky-Zaharov showed, this theory has an infinite number of conservation laws, conservation currents, and the corresponding charges are the tensorial charges of this form. They are constructed at the integral over the three-dimensional space of the Hamiltonian times the number of components of the unit vector m constructed with the from the Poynting tensor. So this theory may be integrable, but I don't know if somebody studied the properties of its integrability in details. So let me just check. Do you hear me?
Yes.
Hello? Okay, thank you.
Yes, yes.
Thanks. Okay, so we see that there is a theory of nonlinear electrodynamics, which is quite specific, but which is conformal and duality invariant. So the natural question is whether there are other theories which have these properties. And it turns out that there is another one, and it is the only one and unique theory, which is ModMax theory, which we found with Ida, Kurt, and Paul. So how this is the unique theory which reduces to Maxwell theory when its coupling constant is set to 0, in contrast to the Belinsky-Zaharov model, which does not contain Maxwell theory in any limit. And the Lagrangian of this ModMax has the following form. So it has the quadratic part, which is proportional to the Maxwell's Lagrangian, and the square root of the fourth powers of F and F dual. Here, gamma is the dimensionless coupling parameter. And if impose the conditions of causality and unitarity, then these conditions require that this parameter is should be non-negative. And of course, one can immediately see that when gamma equals to 0, the Lagrangian reduces to Maxwell Lagrangian. But there is no weak field limit in which the theory reduces to Maxwell theory. This is due to the conformal invariance. Now, let's have a look at the energy momentum tensor of this theory. So the energy momentum tensor is has this form here. It is proportional to the Maxwell energy momentum tensor, and it's traceless. And this is the consequence of conformal invariance. And it has this scalar factor here, which looks quite weird. And we see that this scalar factor is not well defined for the null fields. That is when f squared and f tilde are equal to 0. And that might be a problem in the theory because, as I said, these null fields, they contain the plane waves as particular examples. But here it turns out quite unexpectedly that the Hamiltonian formulation of the theory comes into the rescue, and where the null fields limit is well defined. So let's see how it goes. So again, if we look at the ModMax energy density, so there is this ambiguity in the limit when E squared minus B squared and E times B goes to 0. This ambiguity is not a singularity, it's just an ambiguity which runs between E to the minus gamma and E gamma. So this factor here takes this value depending on how we take the 0 limit. But the energy momentum density in the Hamiltonian formulation, it is just the Hamiltonian. So we perform the Legendre transform of the ModMax Lagrangian in a way which we did in the case of the Born-Infeld theory by introducing the electric displacement vector D here, and then we compute the form of this energy momentum tensor, or if you wish, the Hamiltonian, where we replace the dependence on E with the dependence of D, and what we get is the ModMax Hamiltonian, which has this form here. And you see that the Hamiltonian is well defined for the values, all values of D and B here. And one can also see this by comparing the values of the null fields. So when we impose the condition that the fields are null on the electric and magnetic fields, these conditions translate into the following relation between the magnetic field B and the electric displacement field D here. So they are, so in this case, as one might expect, for the null fields, the Hamiltonian of the ModMax theory reduces to that of the Belinsky-Zaharov. And so this shows that in the Hamiltonian formulation, the configurations of null fields are well defined, and indeed they are exact solutions of ModMax theory, which becomes a non-trivial fact. And among these, we have the plane wave, which we found in our paper with Igor, Kurt, and Paul. And then Bessie and Gavert showed that ModMax also has exact topology between trivial Hopfian-like knot solutions. So this is what I wanted to say about ModMax theory. And I don't know whether if there are questions, should I ask them now? There is some, or afterwards.
Well, I have just a question.
Yes, please.
What about the electron self-energy? I mean, Dirk Born-Infeld is known to avoid issues with electron self-energy. What about this theory?
Well, this theory as it is has this singular self-energy. but we have constructed a generalized Born-Infeld theory, which produces this ModMax theory as a weak field limit. So it's like a Born-Infeld, but it produces not Maxwell, but this ModMax in the weak field limit. And in that theory, the electron self-energy is limited. It's finite.
Okay, thanks.
May I ask a question?
Yes,
I'm Martin. So have you tried or considered the supersymmetric extension of these, or?
Yes, there is a supersymmetric extension of this, n equals 1 at least. We have constructed it with, again, with Igor, Kurt, and Paul, and also Kozenka constructed it independently.
N equal 2 or n equal 4, you didn't try, or
well,
you expect not to work?
Yeah, n equals 4, of course, is challenging. N equals 2, it seems that there is some problem with, we have not studied this. Sergei Kozenka looked at n equals 2 case, and he says that in the n equals 2, for some reason, it's not easy to maintain both the superconformal and duality invariance. But when the theory reduces to n equals 1, it becomes superconformal and duality invariant.
There is a bit of noise, so you can mute your microphones.
Okay, so if there is no other questions, let me proceed. Now I would like to discuss some applications of nonlinear electrodynamics, and in this way I will introduce other models of nonlinear electrodynamics which have been used by different authors. So as I already mentioned, in the last couple of decades, in addition to this Born-Infeld and Heisenberg Euler theories, a variety of other models of nonlinear electrodynamics have been proposed, coupled to gravity and used in different contexts. And the context which I would like to briefly discuss are the construction of new black hole solutions and the study of their properties. So there was a rather intensive activity in this direction with the use of these net theories. Then also people studied whether nonlinear electromagnetic effects can mimic the dark energy and the acceleration of the universe, and explored cosmological models, for example, the possibility of avoiding initial Big Bang singularities. And there has been a rather intensive activity in applying these nets to the models in the context of gravity, condensed matter, holography, for instance, for the describing holographic superconductors, planar mode insulators, and strange metals. Of course, each of these topics, I think, requires a separate talk by an expert. So here I will only flash some basic properties and ideas behind these applications. So basically in this, because we are talking about coupling these linear electrodynamics models to gravity and study in particular black hole solutions in the concept of cosmology and also in the holographic setup. All these constructions, they have a common basis, which can be either the general relativity or even more general so-called modified gravity models, but let us restrict ourselves to general relativity. So what we consider is the coupling of, we consider the Einstein equations in general with the cosmological constant, and which are sourced by energy momentum tensors produced by the nonlinear electrodynamics plus some matter. And also we have the equations of motion for the nonlinear electrodynamics, which may be sourced by electric currents and magnetic currents. And if the magnetic currents are present, then of course there is this necessity to modify the Bianchi identities, introduce, for example, the Dirac kind of strings to describe monopole type objects and all these things. And then in these setups where the black holes take part, one considers, for example, the black hole type matrix of the following form, where Fr and Ur are functions whose explicit form depends, of course, on which matter and nonlinear theory we are considering. And in the simplest cases, one may be interested in the spherical symmetric black holes and study what are the properties of the function of Fr. And in the context of the ADS CFT or gravity CMT holography, one considers the black holes with this term in the metric, which has this form here, where X and Y have the meaning of the coordinates parameterizing the ADS boundary when at R going to infinity, where R is the ADS radial coordinate. So let me give some examples of what was studied in this setup. For example, one of the directions of research was the construction of exact non-regular electric and magnetic black holes solution. The history here is the following, as for example, Penrose showed in his famous paper in 1965 that the gravitational collapse also in general relativity also always produces black holes which have curvature singularities like Schwarzschild or Reiser-Nordstrom, for example. And this means that classical general relativity is not applicable when they approach singularity, though it is covered by the horizon. And then people started to ask the questions whether in principle there may be some black hole solutions which are regular, which don't have singularities of their curvature. And probably the first solution of this kind was proposed by Bardeen and in 1968, and only in 2000, Ion and Beato found the theoretical interpretation for this solution. So Bardeen proposed the metric of this form, where Fr in the metric which I have shown has this form here. And but he proposed the metric, but he did not propose a theory or equations of motion from which one can get this metric as a solution. And it turns out that, as Ion and Beato showed, that the constants M and the Q can be interpreted in this solution as the mass and the magnetic charge of certain nonlinear electrodynamics, whose Lagrangian is very specific one. So the Lagrangian of Ion, Beato, and Garcia, whose energy momentum tensor sources the Bardeen black hole, has this very specific form here. And the electromagnetic field strength of this solution is the standard expression which describes the magnetic monopole with the charge Q. Now, let me also mention that also ModMax effects on the properties of black holes have been studied by several authors during the last and this year. And for example, the deformation of Taub-Nut and Reiser-Nordstrom solutions have been studied, the thermodynamics properties of their thermodynamic properties affected by the ModMax theory. And let me just, for simplicity, show how the Heisenberg black hole solution looks like in the case of Maxwell theory. So the vector potential now has the Coulomb part of the vector potential gets modified by the factor of e to the minus gamma, where gamma is the constant theory. The magnetic part remains the same, and the FR function in the metric of the Heisenberg black hole gets modified in this simple way. So again, we have the two horizons, and the mass squared should be more or equal to the combination of the squares of the electric and magnetic charges of this black hole. But one can see that the extremal black hole, where the horizons coincide, is when the m squared is effectively less than the charge squared of the black hole by the ModMax parameter e to the minus gamma here. So this is an effect of the theory in this case. Okay, let me now consider some cosmological applications, which in a sense are in the spirit of finding the non-singular solutions of the black holes. So people tried to use nonlinear electrodynamics to avoid primordial singularities in the cosmological models, like the Friedman-Lemaire-Robertson-Walker cosmology. And because, again, the singularity of these cosmological models is an important issue, indicating that the classical gravity is not applicable at the early times of the universe life. So in the case of the Friedman-Lemaire-Robertson-Walker, the metric has the well-known form here. And here we have the scalar function AT, and the constant k, which is 1 when the universe is closed, 0 when it is flat, and -1 when it's open. And if the function at has becomes 0 at some initial time t0, then there is a singularity in the solution. And it turns out that the nonlinear electrodynamics may lift this singularity, and a simple example was proposed by De Lorenzi with collaborators in 2002, and they considered models which which look like Born-Infeld or Heisenberg-Euler models up to the 4th order in the field strands. And it turns out that if you take the Lagrangian of this kind and compute the form of the scalar function at t, then we find that it looks as follows. It's the square root of t squared plus the parameter alpha squared here, and you see that the function at t never vanished, and this is an example of the non-singular universe, if you will. Another application is to study the possibility of using these nonlinear electrodynamics effects for accelerating the universe, either by producing inflation or at the later stages to mimic the cosmological constant behavior. And this also has been studied in various papers. So let me just give a couple of examples considered by Novello with collaborators. So what they show that if one takes the Lagrangian, which has this form, then the universe gets accelerated. And another example was by Kruglov, the example of a so-called rational nonlinear electrodynamics with the Lagrangian of this form. And basically the essence why there is an acceleration is the following. In these nonlinear electrodynamic models, the electromagnetic fields behave as a fluid with negative pressure. So if one computes the equation of state between the density and the pressure of this electromagnetic matter, then one finds that for this form of the Lagrangian, they have the following expression, and this is always zero. So in the Friedmann's equation, which is the second order differential equation of A with respect to time, the right-hand side becomes positive, and this signals the acceleration in these models. So this is what I wanted to say as far as the applications to gravity and cosmology is concerned. And if there are any questions at this stage. Okay, just if somebody can answer if you hear me. Please.
Yes, yes.
Yeah.
Okay.
Is Born-Infeld electrodynamics, this last effect does not occur?
In the
accelerated
yeah, well, as far as I know, no.
Yeah,
as far as I can say, yeah. In that case, this equation of state does not have this form.
Yes, thank you.
Okay, let me now pass to the consideration of these gravity CMT holography applications. And so gravity CMT holography is a ramification of a powerful framework which is called ADS-CFT correspondence, which has its roots in string theory and which allows to and provides a toolkit for establishing a dual relation between weakly coupled gravity theory, which is formulated in some asymptotically anti-de Sitter spacetime, and a strongly coupled field theory living on the boundary of ADS. And it prescribes how one can translate the physics, or if you wish, observables or quantities which describe the boundary theory to the quantities which describe the gravitational Bach theory and vice versa. And then nonlinear electrodynamics models has been used in this context for studying, for example, holographic superconductors, and also planar mode insulators, which are materials whose insulator properties are determined by electric current interactions. And these current interactions are simulated in the bulk theory by nonlinearities of nonlinear electrodynamics. And similar things happen in the case of strange metals. Strange metals are called strange because they have an anomalous dependence of resistivity with respect to temperature. Many of them, in many of these models, materials, the resistivity is linearly depends linearly on temperature, while the usual metals depend. In the usual metal, the resistivity depends on the square of the temperature. For all of these applications, again, there is a common holographic setup in which once in the bulk theory considers, for example, the Einstein gravity with the negative cosmological constant, adds the Lagrangian for the electromagnetic fields, nonlinear ones, which may couple to scalars, and this Lagrangian for scalars, and some boundary terms to have the consistent variational problem. And the scalars here may be the axion, dilaton, and charged scalar fields. Axion and dilatons are added, for example, to break translational invariance in the bulk, which by considering their non-trivial profiles along boundary directions, which corresponds to the momentum dissipation in and one of the simple ansatz which one take for a background electromagnetic field is as follows. So one again has a Coulomb potential, electric potential, which depends on the radial coordinate in the ADS space, and then there is a magnetic part which is non-trivial, non-trivially depends on the coordinates xy, which are associated with coordinates of the ADS boundary. And these electromagnetic fields and the scalar fields, they source black hole solution, which again in some models has this usual simple form with two functions fr and ur, whose explicit form depends on the model and under consideration. And the horizon, of course, of this black hole is appears when the function f has a 0, so RH is the value of the radial coordinate of the horizon of this black hole. The black holes play a very important role they are very important ingredient in the ADS CMT holography, because they are thermal states and they have the temperature. This is a Hawking temperature, which is defined as the derivative of F with respect to R. And this temperature corresponds to the temperature of the dual theory on the boundary. And in this setup, the electric current operator in the boundary theory is due to the electromagnetic field on the bulk, and the nonlinearity effects, as I said, they correspond to the current interactions in the boundary theory. And the physical characteristics of the model, they of course depend on the ingredients of the setup and the form of the nonlinear electrodynamics Lagrangian. And for a wide class of models, for example, in a so-called probe field limit, one can compute the components of electric conductivity matrix of the boundary theory material in the following form. So the electric conductivity matrix from the bulk perspective is determined as the components of this conductivity matrix are just the derivatives of the Lagrangian with respect to the Lorentz scalar, electromagnetic scalar S, and the electromagnetic pseudoscalar P here. Then, upon deriving these expressions, one can go ahead, one can compute the electric resistivity and Hall angle, and this becomes a starting point for studying, for example, temperature depending on these quantities, phase transitions, and other properties of boundary theory materials. So this is what I wanted to say about the applications in these ADS CFT correspondence contexts. So if there is any question, we can discuss now. Okay, if not, then let me finish this talk by considering the last point, which is related to some physical phenomenon, which is called Birefringence, which is common to all or almost all models of nonlinear electrodynamics. So Birefringence here is the phenomenon which is similar to what happened in certain optical materials, when light penetrates in this material, it splits by polarization in two different rays, depending on how light is polarized with respect to the axis of this material. And in the nonlinear electrodynamics, the role of this material is played by a uniform electromagnetic background. So the electromagnetic background played the role of the optic material, and the effect of birefringence appears due to the nonlinearities of the theory, and can be computed in this way. So we are interested how to compute the effect of the birefringence. We take a Lagrangian of non-linear electrodynamics and split in this Lagrangian the field strands into the background part, which is considered to be strong with respect to the fluctuations of small fluctuations around this background. And then we expand the Lagrangian to the quadratic order and fluctuations and compute the dispersion relations for example, for linearly polarized waves in this background. And for simplicity, let us take this background to be a strong magnetic field B here. And then what happens is that in general, there are two different dispersion relations whose form depends on whether the polarization of light is along the magnetic field, so it's either it's parallel or perpendicular to the magnetic field, and then there are different refraction indices here, and parallel and orthogonal, which characterize these different dispersion relations, whose form depend on the properties of nonlinear electrodynamics. And the birefringence takes place if the difference between n parallel and n orthogonal is non-zero. In the Maxwell case, of course, there is no birefringence because both coefficients are just equal to 1, and the dispersion relations are those of the light cone. And it turns out that Born-Infeld actually is the only or almost only nonlinear physically meaningful nonlinear electrodynamics where the birefringence also does not take place, because also in Born-Infeld theory, delta n is. In the case of Heisenberg-Euler spinor quantum electrodynamics, this delta n has this value here. It depends on the square of the magnitude of the external field, but you see that this delta n is very small, and it's difficult to determine it experimentally. By comparison, let's have a look what happens in the case of the ModMax theory. In this case, the two dispersion relations are look as follows. There is one dispersion relations for one mode which propagates with the speed of light, the standard one. And then there is the second one, which has the following dispersion relation, where phi is the angle between the wave vector k and the external magnetic field B. The effect is the strongest one when k and b are orthogonal, and then the delta n for the ModMax field is e to the gamma minus 1, and for small gamma it is proportional to gamma. So basically, the birefringence effect measures the value of gamma. And let me conclude here with showing how what are the latest bounds on the value of delta n of the Birefringence from the latest experimental data, which are at least those which I know. They were provided in 2020 by the results of the so-called PVLAS experiment, polarizing vacuum by lasers, which took place in the Legnaro laboratory of INFN near Padua. So that they have not observed the effect but they found these bounds on delta n, and they did not. Probably the reason why they did not observe the effect because the strength of the electromagnetic field which they reached was 2.5 Tesla, which was not enough to arrive at the values which can be those produced by quantum electrodynamics, which one expects from the spinorial quantum electrodynamics. And here one can, of course, see that if ModMax theory has something to do with reality, then, of course, its coupling constant gamma is very small, and one should explain why it happens. But here I should also mention that delta n may be a result of the combined effect of some classical and quantum nonlinear contributions to the Birefringence. So to understand which theory produces Birefringence or not, or a combination of models, one needs also to measure the refraction indices themselves and not the difference between them. And this may tell what the theory, what is the nonlinear electrodynamics which produces this Birefringence effect. So I think I have reached my conclusions, and so let me just summarize what I tried to discuss today. Is that during the almost 90 years of research, nonlinear electrodynamics has been an active area in theoretical physics, and it has applications in the theory of fundamental interactions, cosmology, condensed matter system, nonlinear optics, and plasma physics, which I of course, could have been able to discuss today. All or most of the models of nonlinear electrodynamics should be regarded as effective in theories, and only for few of them, namely for the Born-Infeld and Heisenberg and Euler electrodynamics, we know the corresponding fundamental theories, which are string theory and pH.D. respectively. And it would be, as Gibbons and Herdeyer showed in a paper of 2000, some of these nonlinear electrodynamics may arise as a result of the Kaluza-Klein compactification of a certain multidimensional higher curvature gravity, which in its own turn may be regarded as an effective theory of string theory. And I think it would be interesting also to understand whether there is some kind of fundamental origin of other nonlinear electrodynamics models, and in particular of ModMax theory, whose structure is uniquely defined by the two fundamental symmetries, such as electric-magnetic duality and conformal invariance. And in this respect, one may ask the question whether ModMax may arise as a certain conformal limit of a theory in which electromagnetic fields are coupled to some matter fields, such as axion dilaton-like scalars, and then the latter are integrated out in the effective action, and whether there is an interpretation of ModMax theory and its Born-Infeld generalization in the context of string theory. And this question was recently has been asked by Nastanza, who has shown that the Born-Infeld, the generalized Born-Infeld, which includes ModMax, can be interpreted as a certain brain construction. And so work on these directions and the other applications of nonlinear electrodynamics is continuing, and I think it will be interesting to see the further developments. So thank you very much for your attention.
Thank you very much, Dima, for the very nice overview and talk. So there were already some questions during the talk, but perhaps there is some. Yes, David has already a question. You can just unmute yourself and talk.
I'd like to record a historical remark that came to me from Dirac in 1981, when David Wallace and I had a long conversation with him. And Dirac and Born visited Schrödinger during the war. Schrödinger wrote several papers on linear optics and the Born-Infeld Lagrangian in the proceedings of the Royal Irish Academy. And Schrödinger got very excited that he would calculate the fine structure constant by equating the two theories, and calculated it to be roughly 10 to the minus 2. And Dirac said this was the most exciting time of his life after 1928, because he thought he could make sense of the point electron. But next month, Schrödinger wrote and said, it depends upon the polarization on the helicity amplitudes. The very interesting thing is that precise comparison was done absolutely explicitly in the thesis of Euler in 1935. He writes down the Born-Infeld Lagrangian, he writes down the first order expansion of his calculation, and he observes that the value of the fine structure constant you get from the unpolarized case is 1/81.2, but of course that gets multiplied by 7/4. So that's just a historical remark, and you can look at the two papers in the proceedings of the Royal Irish Academy. They're available online, where you can see that Schrödinger is struggling with this.
Okay, thank you very much. It's very interesting.
Are there any other questions or comments for Dima? So perhaps I have one. So I guess it was already asked a little bit more, but can you say something about something more about what could be, a fundamental theory, like a string-like fundamental theory for this object, for this model, for this ModMax, if any?
Well, it's difficult to say at the present time, but the direction which might take here is, oops, sorry, let me probably show one slide here, if just the Born-Infeld generalization of this model. Oops, sorry, it's, if I can.
You can maybe just show it without the full screen.
Yes, because it is,
yeah.
I will just, so this is how it looks like. So you see that instead of here, in these brackets here, you have the ModMax Lagrangian instead of the Maxwell Lagrangian, which would stand for the usual case. And then the question is whether there is some brain constructions which may reproduce these Lagrangian. And the first steps toward these directions were made by Nastase, who coupled these Lagrangian to scalar fields in a way similar the Dirichlet brains coupled to scalars in the standard Born-Infeld description of the Dirichlet brains. So that's what one may say. And there are some higher dimensional generalizations also of this theory. For example, generalization to the 6-dimensional interacting chiral form, which is written here, but I don't want to explain probably now how the theory looks like. So there is a kind of M5 brain generalization of this modification in 6 dimensions as well. But still.
Okay, thanks. So, are there any other questions or comments for Dima? So, since I don't see any, I would thank Dima again for the nice talk and for answering the questions. Indeed. And once again, I would thank you all for coming, for attending, and remind you that we will have a little bit of a break in our tea break series, and we come back on the 19th of January with a special tea break dedicated to Steven Weinberg and his legacy. And that if you have the time and you're interested, there is going to be a meeting which is both available online and in person at GGI next Monday, Tuesday, and Wednesday, the Avogadro meeting, and you can get the links and register on the GGI website. That being said, it's a pleasure to wish you happy holidays and see you soon.
Thank you.
Thank you all.